I would like to start from the very beginning, so from a very basic question. Why could intermittency and variability represent a problem when talking about renewable energy?
I can take this. I guess the problem comes that when we have these renewable resources like wind and solar PV that are weather dependent, they depend on the weather and the season, and for example time of the day if we are thinking about solar energy. So when we have these technologies, they might generate electricity at times that we might not need, or our needs are not that high. So we need different measures, different solutions to help us to match the generation of electricity from these resources that are not controllable. They produce electricity at any time that there is wind or solar energy, sun in the sky. And it might be that this is not the right time for us to use that electricity. So we are thinking about different options to store electricity, to shift electricity from one time to another.
Yes, I get it. And so talking about your specific study and your project, what's the idea behind this underground gravity energy storage system, and how does it work?
I can go with that. Yeah, I can go if Julian, okay. You said your connection might be shaky, but please chime in, Julian, if I missed something. Yeah, the idea here is that we need electricity storage, and for future systems, future societies that we want to reach to almost zero carbon, we want to have a lot of renewable energy, a lot of wind and solar PV, and as such, we need even more energy storage. Until today, energy storage was mainly based on using batteries or pumped hydro storage. These are the two mostly used commercial technologies. But we know that, for example, batteries are not suitable for long duration storage. We cannot use batteries, for example, to store electricity for weeks or months or seasons, because batteries get depleted, they have self-discharge. Also, pumped hydro is very site-specific. It requires a mountainous topology, and it's not very easy to build this technology in each and every country. So the solution that we are proposing is actually based on using underground decommissioned mines. There are many mines. We estimate more than 2 million mines around the world that they are depleted or they are decommissioned, meaning that they are not operating anymore. But there is a whole infrastructure there underground, and these mines can be used for storing electricity. And how we can do that? This is based on the concept of gravitational energy storage, meaning that you can lift a weight, and when you lift it, you convert energy to potential energy, and you store it in a higher, reservoir or a higher level. In this case, what is happening is that you can store sand on top of a mine or outside the mine on the surface. And then whenever you want to, for lifting the sand, you need electricity. And that is when there is a lot of extra electricity in the grid, or electricity is cheap. You can lift the sand, put it up there on the surface. And whenever we need electricity, let's say 2 months later, 3 months later, or even longer, we can descend the sand, or we can, bring down the sand through a shaft, through a mine shaft, which using a technology called regenerative braking. This weight, when it's coming down, it generates electricity, and that can be used for the grid. So this is the cycle. For charging, we use devices, buckets, conveyors to bring the sand from the mine to the surface, storing there. And whenever we need electricity, again through the same shaft, we descend the sand, and when it's coming down, imagine a heavy mass is coming down, and we can use the regenerative braking to generate electricity.
Great, it's really clear. And so what benefits does this system have in terms of costs, efficiency, and environmental impact?
Julian, would you like to go ahead? If not, I can.
Julian, can you hear us?
Yeah, the main benefit is to, yes, so sorry, it might be a bit delayed here. So the main benefit is to store energy for a long term. And for that, you need to have the demand for long-term energy. And the main benefit from long-term energy is to be able to scrap fossil fuels forever, so not have to rely on fossil fuels. Now, today that we have gas, oil, it's difficult to make seasonal storage viable. It's only viable with, for example, hydropower, pump storage, and yes, so, but of course you don't have potential for hydropower pump storage to cover all the energy storage needs in the world. So this underground gravity energy storage is another solution that can provide these services. And the idea is to store energy for a couple of weeks, months, for seasonal storage. So storing energy from the summer when you have a lot of solar power, when demand for electricity is low, and then you generate electricity during the winter when you don't have so much solar power, and when the demand for energy is high. This is an example. So in locations where you have this need to store energy for long term, for one season to another, maybe even for 1 year to another, then this underground gravity energy storage solution makes sense.
That's clear.
Maybe if I can add a couple of also points that it might be useful to repeat, talking about the environmental benefits. As Julian mentioned, this technology doesn't need any fuels. I mean, that is, I would say, the first thing to keep in mind. But also it's not so material intensive like batteries. For example, if you remember last year in 2022, the cost of batteries increased for the first time. We always observe that the cost of batteries are declining, but last year it increased because there was a lot of demand from mobility, from other applications for batteries. But this technology doesn't need any material. It's sand. Actually, sand is the most maybe abundant material. One of the most abundant materials on Earth. So it doesn't have any environmental impact in that sense, no emissions, no material intensity, it's completely clean. And also if you think about these mines are already there, so you don't, you don't do excavation, you are not, for example, changing the, any space or land in any area. These mines are usually, even sometimes they pose some hazards and risks to the society because there is a risk of collapse of the mine, explosion. Someone needs to be careful that the road that goes to next to the mine, it doesn't get landsliding or other problems. So in principle, when we use these mines, it's also good because it reduces the risk of or other environmental problems that might happen. One thing that might be very interesting to you is that some people ask why using sand instead of water, because in principle, in some of these mines, it might be possible to use water for such a for electricity storage. But one thing is important to know is that again, water might contaminate or gets contaminated when it's in touch with the soil, or there will be leakage of water. The water goes to underground water, and it might be some other problems like bleaching, or when things become difficult in a mine in the underground. But most of the mines, especially these mines that we are talking, these are the equipment, the environment is very compatible for using sand. You don't have to do too much refurbishment, changing the functionality of the mine. The buckets, the devices, they were used to, for example, carry coal or other minerals, and now they carry sand. It's very, I would say, convenient to change the application of these mines.
But what amounts of sand are needed? Because you said that it is a really abundant resource, but maybe is not renewable in a certain sense. There are articles that say that also sand is a precious resource that we should not waste. Maybe it is not the case, but I wanted to solve this doubt that
that's a good point. That's a good point. We should be clear that the sand is not getting wasted. Sand just goes from lower part to the upper part and then to the lower part. So there is no evaporation, there is no dissipation of sand. So sand is always there. There is zero waste of sand. There might be, of course, I don't know, very, very little sand getting there and there.
Yeah.
But please, Julian.
Can I answer? Sorry, there might be a delay there. I participated on a paper called Sand Depletion, and this is a major issue because there is a lot of rivers being dug to extract sand, and they just have a huge environmental impact. And there are even conflicts that arise from sand, conflicts in India, in Pakistan, and for example, the sand is used to create concrete. Concrete is the third largest commodity used in the world. It's huge consumption. It's also used, for example, for creating those islands in Dubai, and to increasing land reclamation in Singapore. And so the demand for sand is huge, and it's a huge concern. The advantage of the technology that we propose is that actually this riverbed sand, which is appropriate to build concrete, is not good for underground gravity energy storage. The good sand for underground gravity energy storage is actually desert sand, which is round, which is very easy to maneuver, which is not compact. So we don't want compact sand. We want sand which is desert sand. And desert sand is not under threat, is not a problem, and doesn't relate to all these issues with sand depletion that has been a concern recently.
That's great. Yeah, that's what I wanted to hear. And which countries do you think would be best to develop this system? I read that maybe the most of the potential is concentrated in China, India, Russia, and the USA. Is that right?
Yes, China has a huge potential. USA has a huge potential. So this would be applied in locations where, for example, you don't have so much water available to store energy seasonally with pump storage, which is maybe 1/2 or 4 times cheaper to store energy seasonally than this gravity energy storage solution. So this is in the supply side, it's in the potential side. So locations where you can't build pump storage sites. And for another locations is, for example, very plain locations where you don't have mountains. So you don't have water, you don't have mountains, you have this option. The other one, looking at the demand side, you have to see at a location where you have demand for long-term energy storage. For example, they have a lot of wind power potential, which varies monthly, weekly, seasonally, or for example, they have a lot of solar power potential in the summer, but their highest demand is in winter, and then they need to store energy seasonally. So, for example, locations is China, US, the western and eastern part of the US, because eastern part of the US doesn't have so many mountains. Western part of the US doesn't have water, but more to the north, because the south of the US, they have most of their demand is in the summer. For example, in Las Vegas, in Los Angeles, they have a lot of air conditioning demand, and then the demand is highest in the summer. So that doesn't help so much. That doesn't increase the demand for seasonal storage if you're generating energy with solar panels, for example. Of course, here we are always considering the fact that countries will supply their energy with solar and wind. If you have coal or natural gas, then you wouldn't even consider this solution. So yeah. So locations where you have deep mines, you don't have potential for pump storage, and you have demand for seasonal storage.
Okay, great. Thank you so much. I have just one last question, because you talked about batteries and hydropower as ways to store energy. But what about green hydrogen? What do you think about that? Because we are talking a lot about it, and we know that the European Union wants to invest a lot in that. So what do you think about that opportunity as well?
Maybe I can take that. In this analysis, we haven't compared this solution with other alternatives. It's because it requires a different setup, to look at each system and see, for example, how these different technologies interplay. But maybe just as a personal opinion, it's not based on the paper, it's my own personal opinion. Hydrogen requires a supply chain, from generation to transmission, distribution, storage, and even end-use technologies. So it's a whole, different infrastructure, and that is probably one of the barriers that has, decelerated the transition to a hydrogen economy. Because, for example, if you can generate hydrogen cheaply, it doesn't mean that you can easily use that. You need transportation, you need also to adopt the end-use technologies. But the good thing about such technologies like this one, underground energy storage, is that first of all, it doesn't depend on any other technology. So in most cases, these mines are already connected to the electricity grid. So you don't need even to, for example, extend the electricity grid to the mine or to make roads, because there has been probably some roads that the cars could come there. So I would say it's not complicated, as opposed to hydrogen, which in general is a complicated energy carrier because it requires changes. For example, imagine if you want to make the cars working with hydrogen, you need hydrogen fuel station, you need to think where to generate hydrogen and bring that. But this technology is directly connected to the electricity grid. it reduces the complexity and losses, for example, compared to hydrogen, that you have to convert to hydrogen, then bring that hydrogen to the end use, then again convert it back, for example, to electricity.
Yeah,
Opening up to Bernard's comments. So the efficiency for hydrogen, it's around 30%. So for you to produce hydrogen, store hydrogen, and then generate electricity with the hydrogen, it's 30%. This underground gravity energy storage varies from 60 to 80%. So you have significantly higher efficiencies for recovering the stored energy.